the same thing. Yeah.
Yeah, it's not on the wall. I can take it off. Global anomaly. Yes. Sweet. Nice.
So you can classify different states by what kind of topology.
Nice. Yeah. So
Okay, but
topology is basically
Okay, so I'd like to welcome our next lecturer, who will be Chetan Nayak from Microsoft Station Q and UC Santa Barbara. He's going to tell us about effective field theory for topological phases.
Okay, thank you. So I want to start out by talking about one of the, maybe the simplest example of a topological phase. So this is the Toric code Hamiltonian. First written down and discussed in this particular way by Alexei Kitaev, although there were earlier works on Z2 gauge theories, going back to work of Wegener and explained quite nicely by Fradkin and Schenker in the late 70s. So the Hamiltonian for this, so this is a system of spins on a lattice. Okay, so for simplicity, I'm just going to draw the square lattice, mostly because I'm bad at drawing other lattices. I'm going to focus in these lectures on two-dimensional topological phases. So if I ever forget to say 2 dimensions, feel free to remind me. It's a system of spins where the spins are living on the links of the lattice. Okay. And it's a sum of 2 types of terms. So sum over all of the vertices of this lattice, okay? And then it's a product of sigma z's around a vertex. So I is in the neighborhood of some vertex. And then there's, so let's call these vertices V. The i's are living in the neighborhood of a vertex V. And then there's a Plaquette term, sum over Plaquettes P, product sigma x I, where I lives on that Plaquette. So here is a Plaquette. And so when the Plaquette terms includes the sigmas for these 4 spins over here. Okay, so this is a Plaquette term P, and here's a vertex term V. Okay. So the nice thing about this model is that it has a topological ground state, it's in a topological phase, and also it's exactly soluble and very simple. Okay. The drawback is that it has 4 spin terms, so it doesn't look like the simplest things that we write down to describe magnetic systems whose low energy degrees of freedom are spins on a lattice. But let's worry about that problem later. Okay. So you can see that this is let's call such a term A sub v, and terms like this B sub p. So for every vertex, you have a term that's a product of the 4 sigma z's around that vertex. For every plaquette, you have a term. It's a product of the 4 sigma x's around that plaquette. And property that this Hamiltonian satisfies, that these operators satisfy, is that they all commute. So any 2 vertex terms commute because they all involve sigma z's, and sigma z's all commute. Any 2 plaquette terms also commute. Okay, and moreover, any vertex in any plaquette term also commute. So these things are all equal to 0. Okay. The reason that any 2 vertex terms commute is because sigma z's always commute. Any 2 plaquette terms commute because sigma x's always commute. The reason a vertex and a plaquette term always commute is because if the vertex and the plaquette are disjoint, then they'll certainly commute. If they're not disjoint, such as if I had this vertex term and this plaquette term over here, okay, well, you can see that they'll share exactly 2 spins. Okay, sigma z's and sigma x's anti-commute. So if you share 2 spins, then that's 2 anti-commutations you have to do, and you get 2 minus signs. So therefore, they commute. Okay. Okay. Any questions so far? I'm sure many of you, at least some of you, have seen this before, but I think it's helpful to review it just so we're using the same notation. Okay, now, so the ground state, so given that all these operators commute, okay, moreover, these operators all square to 1, okay, because the sigmas all square to 1. So these numbers, these operators all square to 1, so their eigenvalues are plus or minus 1. Okay, so we can trivially diagonalize and find all the eigenstates as Hamiltonian just by specifying the eigenvalues, which are plus or minus 1, for each of these commuting operators. Okay. In particular, the ground state is a state in which all of the eigenvalues are plus 1. So for all vertex operators, all Plaquette operators, they all acting on the ground state give you plus 1. Just a second, I see your hand. As a result of that, the energy is equal to minus J1 times the number of vertices minus J2 times the number of plaquettes. Okay. Now we have to be a little bit careful if we're on a lattice with boundary, about what we do about the boundaries, and or alternatively, if it's on a surface with non-trivial topology, we have to be a little careful, and as I will momentarily. Yes, there was a question? Well, I'm not sure what would count as intuitive. The Hamiltonian is a sum of commuting operators, all of whose eigenvalues are plus or minus 1. So if you want to, you can therefore diagonalize each of those operators separately. And so this is just a thing that minimizes the energy. If any eigenvalue was minus 1, the energy increase would be, depending on whether it's a vertex or Plaquette term, you would increase the energy by 2 times J1 or 2 times J2. Okay. Yes, assuming these are both positive. Good. Any other questions? Okay, so I think I can give a slightly different answer to your question about intuitive by introducing an intuitive way of thinking about the ground state and also the excited states. Okay, so anywhere on this lattice, okay, so if I take a look at any configuration of the spins, then we'll have configurations of spins that look like this, say. Then what we're going to do is any place that we see an upspin, we're going to color in that link of the lattice. Okay. Okay. And any link that has a downspin, we're not going to color in. Can everyone see yellow? Should I use blue instead? No. Blue's better? Okay. Okay. So we're going to color in those links to the okay. Blue equals upspin, sorry. Okay, so we'll color in where all the blue spins live. Okay, if we do that, then when this vertex term is equal to +1, what it's telling us is that there have to be an even number of upspins around that vertex. Okay, because AV is the product of the sigma z's around that vertex. It's an even number of upspins around the vertex, which means that the curves that are formed, or the piecewise linear curves that we have on this lattice, that these curves don't terminate. Okay. Since you can have, at any lattice, you can have 0, 2, or 4. If you have 0, it means that you don't have one of these curves touching that vertex on the lattice, a blue curve. If you have 2, that means that you have a curve that touches and it continues through, like as shown here. So the curve just continues through that point. And if you have 4, it means that you have 2 such curves crossing. So if this spin were flipped up instead, and this were up, then you would have a situation like this. Now, there might be circumstances in which you don't, it's not the case for this model. There might be circumstances in which you don't like having curves touch in other models that we might want to employ such representations. You can avoid that by by resolving these points on the vertex, or for instance, just working on the honeycomb lattice instead. I could have done all this on the honeycomb lattice and never had to worry about curves crossing. But I wanted to work on the square lattice since the original paper of Kitaev works on this lattice. But that's maybe more of a statement for the experts, I guess. So, but for now, let's just continue. So what these terms tell us is that we can represent the we can represent all the states that satisfy that the A term has eigenvalue +1. All such states can be represented just by a configuration of closed loops, possibly intersecting on the square lattice. Okay. Okay, so that's sort of half the problem of diagonalizing this Hamiltonian, is to understand all the AV terms. We also have to understand that the vertex terms, the Plaquette terms. I should also say that any V such that AV equals -1, okay, if there happens to be, so that's an excited state above the ground state. Any such state is a place basically where a curve terminates, okay? So here's a situation like this. That's an excitation where one of these curves terminates, okay? So AV equals -1 also allows, of course, 3 curves to terminate at that point. So you might instead, if I flip 2 of these spins, have a situation like this. Okay. Both of those are equivalent types of excitations. You could think of this, if you wish, as a closed loop over here, and then another one that just happens to terminate at the same point that's going through. Okay. So that's the way to think about these vertex terms, is that they're basically enforcing the relation that the low energy states, for instance, if we took the limit where J1 was much, much larger than J2, then we'd say we had a low energy subspace of the total Hilbert space, which is just composed of closed loops on the lattice, okay? And to get out of that low energy Hilbert space, the excitations are basically anytime you have a curve that terminates at some point. You can also see, therefore, sorry, do you have a sorry, let me just say one more. You can also see that to get such an excitation like this, you have to create them in pairs, okay? Because if you have a curve that has one endpoint, it's going to have another endpoint. Again, modulo issues of what maybe happens if it's a lattice with a boundary. Okay. Yes.
Like different configurations of these closed curves.
Yeah.
You think of them as like inequivalent states?
Yeah. So far. Yeah. So these are all spins. So if I just color in the blue links whenever I have an upspin and leave it uncolored where there's a downspin, that's just a graphical way of representing the natural sigma z basis of the total Hilbert space, right? So far that's just a graphical way of representing all the basis states, or a particular choice of basis states. Now, if we make this restriction to closed loops, then it's a subspace of that. Again, this is a natural choice of basis states for that subspace. Okay. Any such state with some configuration of closed loops is not going to be left invariant under these terms. Okay, so those are the terms we're going to now start talking about. Any other questions? Okay, so good. So that's what the vertex terms tell us. Now the Plaquette terms, if you think about what a Plaquette term does, it's a product of sigma x's. Sigma x acting on a downspin flips it to up, acting on an upspin, it flips it to down. So what a Plaquette term does is it takes some configuration such as this around a Plaquette and transforms it into this. It flips those upspins and it flips the downspins. Okay. What you can see, if we go back to this graphical representation, what it does is it takes this loop configuration and transforms it into this one. Okay. What you can think of that as doing is it's taking some, and this loop presumably continues on in some other way, outside, beyond that Plaquette. What it's doing is that Plaquette flip operator is taking the loop and it's just deforming it. Here's a loop that kind of does a little curve over here. You act with that Plaquette flip operator and it deforms it so that it moves over here. Right. Now I've drawn the case for what it looks like when you take a Plaquette that has 2 neighboring upspins and 2 neighboring downspins and flip them. But there's also obviously cases in which you have all downspins on a Plaquette they get flipped to all up spins, or vice versa. We can represent this graphically as saying that what it does is if I now stop drawing the spins, and in fact also stop drawing the lattice, and just draw these as curves in the continuum, then what this operator does is actually maybe I should use blue for consistency. Is it takes a little bit of one of these curves and transforms it into this, and vice versa. Okay, so this is a case in which a given plaquette had only one upspin. That upspin gets flipped down, and the downspins get flipped up. Okay, it also does this. If you have two, well, actually, maybe I want to show the thing that I showed over there. If you have this is the thing I already drew for you over there. This is turned into this. Okay, so yeah. If you have a plaquette where all the spins are up, they all get flipped to down. So this is the empty picture. Maybe I'll draw the 4 vertices over here. Okay, and then the last thing that happens is if you have a plaquette with parallel sides have up spins and the other 2 parallel sides have down spins, this becomes this. Okay. So that's what the Plaquette operator does, the Plaquette flip operator. Questions? Okay. So now, another way of saying this, or rather a way of saying what this tells us about the ground state, is that if I look at the ground state wave function, okay, what the ground state wave function has to satisfy, if it's going to be an eigenvalue, if it's going to be an eigenstate of that flip operator, is that when you evaluate the ground state on any one of these pictures, okay, where a picture is just a collection of closed loops on the lattice, possibly intersecting closed loops on the lattice, that ground state has to give the exact same amplitude for any pictures that are connected by these moves. Okay. So in particular, if I see some curve, so I'm not drawing the rest of the picture, I'm just drawing a piece of this, then the ground state has to have the exact same value, has to assign the exact same amplitude to this other curve. Okay. No, not any eigenstate. The ground state has to. If you excite the system so that some, and I'll come to excited states momentarily. If you excite it so that some of these operators are frustrated instead, then there will be some plaquettes somewhere in the lattice for which this is not satisfied, and for which, in fact, it has to have a minus sign on the other side if it has eigenvalue -1. Okay, so this is basic. So in going to the world of closed loops, that was let's assume for a moment that J1 is much larger than J2. So if we restrict ourselves to closed loops, then that's basically saying all the states that have energies much less than J1. And then of course there's J2, and if we're separating out the ground state from stuff that is higher in energy by J2, then we have to impose conditions like this. Okay. Yes. Equal. BP has eigenvalue plus or minus 1, so the only possibility is that it's equal or -1. Okay. And -1 will be an excited state, and we'll talk about the excited states momentarily. Okay. We also know that anytime you see a closed loop, it should have the exact same amplitude as this empty picture. Okay, and the last thing is that anytime two curves come close together, that we can, this is, you might call this perform a surgery, which is you take, I mean, the rest of the picture is unchanged, but we basically cut these two curves through here and rejoin them in the other way. Okay. Yes?
Given an explicit rule that describes the amplitude of all the states?
Yes, it is. The rule is the amplitude is 1 for all possible closed loop configurations. Yeah. And these rules allow you, well, depending on what you prefer to do it by drawing pictures or by solving equations. I mean, this statement that the eigenvalues of all these operators is plus or minus 1 also tells you that the amplitude is 1 for all of these. You can alternatively, sorry, I should have used blue here. You can alternatively look at these rules and show that these rules allow you to reduce let's for the moment, now we have to talk a little bit about the surface we're on, but for the moment, let's imagine, let's consider the torus, okay? So since we're talking about the square lattice, the easiest okay, so torus just means periodic boundary condition. Okay, we take a square lattice, put periodic boundary conditions in both directions. Let's in fact consider just the square torus for now. Okay. So this side is identified with this side. This side is identified with that one. Okay. Yeah, let me just make one more comment. Actually, let me backtrack for a moment and make one comment about related to Nick's question, which is there only one eraser? Oh, there. Okay, great, thanks. Yeah. In writing down an expression like this for a wave function, what I'm doing is I'm taking a state of the system and I'm expanding over all possible configurations of closed loops, okay, in a basis of kets where each ket is associated to some closed loop configuration. Okay. Actually, we can go further. We don't have to restrict ourselves to closed loops. It can be any one of these configurations of curves. Okay. But for low energy properties, so again, let's assume that J1 is going off to infinity. We only want to consider closed loop configurations, possibly intersecting. Then in such a case, this is a basis of all the states with energies much less than J1, right? Is a closed loops. And if we consider, when I write down that there's some wave function like that, what I mean is I'm taking an arbitrary state, I'm expanding it, and the psi sub c's are the coefficients in that expansion. Okay. And what we're saying is that these psi's have to satisfy some relations. Yes.
Also, by you denoting all the spin configuration by blue lines, you're assuming also along the one line it goes pointing up, but with not have up with state A and B.
No. These are just basis states. This is just basis states. Of course, I can superpose these basis states with any phases I like. So I'm not making any assumptions about the.
It has to be uniform along the line, correct?
in this particular choice of basis. Yeah, but of course I can make superpositions with arbitrary phase. Those will come in over here. Okay, these are arbitrary complex numbers. Okay. Yeah, I mean, yeah, they're arbitrary complex numbers, and then if we also require that if we start now asking what happens, what the ground state looks like, then they also have to satisfy these conditions. But for J1, again, going to infinity, if we don't look only at the ground state, then these are arbitrary complex numbers. Okay.
So
Yeah.
the reason, just to clarify, the reason they have to be all equal, those conditions, is because when you have BP at psi and the ground state,
Exactly.
reshuffle that you just want it to reshuffle
Exactly.
one coefficient.
Exactly. So this condition that BP has eigenvalue 1 is exactly equal to these, implies these relations. Right. Okay. Okay, so now, supposing we're looking at the torus, okay, and we have some configurations of loops. Well, what you can see is what those three relations up there allow you to do is they allow you to take any configuration of loops. Okay, so if I have any loop that's contractible on the torus, so I take any loop like this. Well, you can use the first relation, which just allows you to continuously deform it. I can continuously deform it until I shrink it down to the size of one plaquette. And then I can use the second relation that says, well, if I have a small loop, I can just get rid of it. Okay? So deformable So when I write equal, what I mean is that the ground state wave function has to give equal amplitude superposition. So it's equal to nothing, okay? An empty picture, okay? So this really means psi evaluated on this is equal to psi evaluated on this, okay? So again, just to repeat, any contractible loop on the torus, I can use the first relation over there to shrink it down. I can then use the second relation to just to erase it, basically. Okay. So the ground state wave function has to give the exact same amplitude for this as it does for this through a sequence of those continuous deformations, and then this I can just get rid of. Okay. So the only thing we have to worry about, therefore, is the non-contractible loops. Is that clear? Okay. So now if we suppose we now look at a non-contractible loop. Suppose we have a pair of such non-contractible loops. Okay. Well, the final relation, the surgery relation, tells us, look, anytime you have a pair, you can redraw this with no change in amplitude. So the amplitude on such a picture has to look just like the amplitude on a picture like this. If you remember what the last picture tells you, anytime you see two curves coming close, you can cut and rejoin them like this. Okay. But you see now, because of the periodic boundary conditions here, this is actually a contractible loop. Okay. So you can also shrink this and get rid of it by moving this one around the other side here, come back and shrink it down. Okay. So this is also equal to whatever that amplitude happens to be for the empty picture. It's the same amplitude you have for any set of configurations of closed loops. I only drew one here, but it can be any arbitrary collection of closed contractible loops here. We'll have the same amplitude as for the empty picture. And similarly, for something like this, where you have two lines going, both winding around the same direction of the torus, you can also contract and annihilate those. Okay. So far we've reduced the amplitude on most of these pictures to just the amplitude for the empty picture. The one we have to worry about is, or not worry about, the one that we can't, or the types of pictures that for which we can't do that are okay. So now, on the other hand, if you have just one line going across, okay, well, there's nothing we can do about that, okay? To apply surgery, which would enable us to contract, let me do a better job of erasing. Okay, so to apply surgery to this, we would need two lines. We have only one line here, so we can't. So this is actually an independent amplitude. Okay, there's no way to relate that to the empty picture like we could over here. So we have an independent amplitude here. And you can see by applying similar reasoning that the other pictures that we have to worry about are. Now, of course, this picture has to have the same amplitude as this picture plus any number of contractible loops on top of it. Okay. So when I draw one picture here, what I really mean is this picture. This particular basis state has some amplitude in a ground state wave function, and as does any other picture obtained from this by applying the rules. There's a similar picture like this, with a line going across the other way, and there's finally one more. Independent picture that looks like this. Okay, which wraps both ways around the torus. Yes? No, you can't turn this into this. If I draw the torus out, okay, one of those pictures looks like this, and the other picture looks like this. And there's no way to deform this picture into this one. Okay. What's that? And yeah, and there's also one in which the last one is I drew it like this. But of course, actually, I did this just for the sake of purists. Since we certainly in this theory allow intersecting lines, I could have just as well drawn the last picture like this and had lines going across both ways. And I could have just done this. Okay. This picture can be obtained from this picture by continuous deformation that just moves this part away. Okay. Because the rules of this model allow for intersecting loops. Just a comment for the experts that sometimes you work on the honeycomb lattice where curves can't intersect, so you would have to draw pictures in the way I did it. Or there may be very different models, but sort of with a similar flavor, for which you don't want to allow intersecting loops. So again, there may be reasons. So just for the sake of purists, I drew them with no intersections, but it's perfectly okay for this model to draw it with the intersections in, like this. Okay. I mean, in some sense, the underlying reason why it's okay to draw, or an underlying reason, is that this surgery tells you that if you have a crossing, it doesn't matter which way you choose to resolve this. You could resolve it like this. You could resolve it the other way. The surgery rule tells you that the amplitude has to be the same in the ground state for both of them, so it didn't really matter. So that's, in some sense, why it's perfectly all right to draw everything with crossings in. Okay. Any questions? So what this shows us is, since the amplitudes are totally independent for these, that there are in fact 4 distinct ground states. Okay. So if you want to think, this is maybe a slightly different answer to an earlier question. If you want to know sort of intuitively what the ground states are, the ground states are just equal amplitude superpositions over all loop configurations, okay? Modulo the issue that you have to specify what the winding numbers mod 2 are around, if you're on the torus, what the winding numbers mod 2 are around the 2 directions of the torus, okay? Once that's specified, it's then an equal amplitude superposition over everything that's obtainable from it by those rules. Okay? The energies are the same. The energies are the same because the energies are all because they satisfy all the terms in the Hamiltonian. Okay, all these states are eigenvalues of all the vertex operators and all the Plaquette operators. So the energies are minus J1 times the number of vertices minus J2 times the number of Plaquettes.
So even
Okay.
there's no even for a finite system, there's no.
That's right. For this particular model, there's no splitting whatsoever. Okay, that's a special feature for this model. Okay, and as we continue, we're going to see that they won't, in general, be exactly degenerate. Okay, I mean, Nick also mentioned this earlier this morning, but for this model, these are all exactly degenerate, regardless of system size. Okay. Yes. Oh yeah. So I mean, so in particular, if I were to just add to this a small term like, well, sigma z or sigma either one, okay? If I added a small h, longitudinal h term, we'd find that these states aren't all exactly degenerate. This hz term basically penalizes having up spins. And as you can see, the pictures that have non-contractible loops are going to have, on average, it's a superposition over many states, they'll have on average a few more up spins, and there will be a small splitting as a result. Okay. And we'll talk about the nature of that splitting a little bit later. Okay. I think was there another question? Yes. Yeah.
So the 4 ground states are the ones for which these amplitudes, like one of them is 1 and the rest is 0.
That's one basis of the 4 ground states. That's the most natural basis. Yeah, there are 4 linearly independent states here. You're free to choose the basis you like. That's one particular basis. Yeah. Yes.
Just to connect a little bit to what Nick finished with about the creating excitations and so the way you.
Yeah, let me talk. Actually, I'm just about to get to excitation. So you want to hold that question until because so far I've only talked about ground states, and the very next thing I'm going to talk about is excitation. So.
I guess just to anticipate that.
Okay.
Briefly, so you, the way you mentioned, you already mentioned excitation a little bit. You flip a spin and you create 2 of them.
Yeah.
In pairs. But Nick talked about it, creating one excitation and a twist. So I guess I was just going to push on you because it's a concrete model.
Yes.
You could make. It would be helpful then. You have an opportunity to really make it concrete with it.
Okay, you're right. I agree. I will make it concrete. Yeah. I mean, we're about to talk about the excitations momentarily. Yeah.
But also, maybe I should have been more explicit, but I was talking about creating one in infinite systems.
Or a system with a boundary, where you have to put something on the boundary also. Yeah. Yeah. Yes. Mm-hmm. Yeah, I mean, I chose to work. I mean, it was entirely a choice. The order in which I did it is I sort of said, let's imagine J1 very large. So we'll first consider all of the eigenstates of the vertex operators and draw and sort of color them in. I could have gone from the opposite limit and said, hey, let's just focus on the low energy space of eigenvalues of Plaquette operators, and then I would have drawn in closed loops on the dual lattice, corresponding to the opposite thing. So it's entirely a choice. I chose to do it this way. Actually, I think it's the case if you look at Kitaev's original paper. I think he actually put sigma x's here and sigma z's here. So, I mean, there are a lot of ways of rewriting this model that are all kind of slightly different, but yeah.
This way of obtaining the ground state doesn't depend on
No, does not. That was just a pedagogical choice. Once you see the ground state, and we're about to talk about the excitations, there's no approximation involved. No. And the reason is because all these operators commute with each other. If they hadn't commuted with each other, then you would be making some approximation. But since they all commute with each other, they can be simultaneously diagonalized. There's nothing essential about making J1 very large. Okay. Yes? Yeah. Correct. Yeah, so there's a lot of ways of generalizing this. It's indeed the case. Because these operators are all simultaneously, I could have put this inside the summation and put a V superscript here and put a P superscript here. They don't have to be uniform actually, they don't even have to have the same sign, but let's make life simple. Let's consider the same sign, but random in strength. This would still be the case as long as none of them were ever 0. You also are not limited to working on the square lattice. Actually, any lattice would do, okay? You just have to be a little careful if the lattice has coordination number that's odd. Then you may want to reverse the sign of this if the coordination number is odd to enforce the condition that an even number of upspins is sitting around a vertex. Other than that, you could in fact make the lattice irregular. It's not essential that it be a regular lattice. So there are because this model is so simple and exactly solvable, there are, and is a sum of commuting local terms, there are many ways there are many variations on this model that basically have the same physics and are also soluble. Okay. Yes? Well, it's no longer exactly, so for this not equal to 0, the model is no longer exactly soluble, okay? This is a small perturbation. You could try to consider it in perturbation theory. You could also numerically study the problem. What you'll find is that you encounter a phase transition at some finite value of this, okay? But in the meantime, for very small values before you encounter that phase transition, so I introduced it in answer to Leo's comment, which is if you do introduce a term like this, and it's small enough that you haven't encountered that phase. Eventually, if this is cranked up enough, it will just polarize all the spins. You'll undergo phase transition to a fully polarized trivial state. But before that happens, what it does is it introduces a small splitting, which is exponential in the system size. It won't be exactly soluble anymore, but you can numerically solve it. Study it, I should say. Okay, so now, so those are the ground states. Now you can also see, by extension, so I did the torus here, but you could also consider other surfaces, okay? So we could consider instead of the torus, we could consider something with genus 2. Actually, we could go backwards. We don't have to study genus 2. We could just study the infinite cylinder. Okay. If you study the infinite cylinder, then you can see that you have to consider winding numbers around there. Okay. Well, actually, let me retract that. Infinite cylinder is basically the torus. Let me not talk about the infinite cylinder. We will come back to the finite cylinder momentarily. Let's consider instead this. Something with 2 handles. Okay. So we'll look at genus 2. That's also going to have degeneracies corresponding to that winding number mod 2. You've also got that. And so on. So you can convince yourself that the degeneracy, by drawing pictures like this, that the degeneracy is going to be 4 to the genus of the surface. Okay. In particular, it's an example of a system in which the ground state degeneracy is determined by the topology of the surface that you put it on. Okay. The two-dimensional surface, again, we're talking only about two-dimensional topological phases here. So the ground state degeneracy is determined by the genus of the surface that the system is living on and nothing else. Okay. Okay. Doesn't depend on any other. Well, yeah. Let me just leave it at that. Okay. So this is sort of one of the features of topological phases, which is that ground state degeneracy determined by the topology of the surface that the system is living on. It's also extremely informative to think about what the excited states look like. Okay. So the excited states, as we discussed, are just places where, so excitations okay. So excitations are somewhere where a vertex operator is frustrated or a Plaquette operator is frustrated. I mean, actually, both can happen. You can have a location where you have both a Plaquette and a vertex operator frustrated. Actually, so these will have, also a pictorial representation. So a vertex operator, well, it's just an endpoint of one of these loops. So you have a whole bunch of loops in your picture. Okay. And if you break a loop, which you will do by flipping one spin. So if you flip one spin, you break a loop, and now you have two loop endpoints at neighboring vertices of a lattice. You can then, by continuous deformation, move one away. That doesn't change the energy. And so I can put these two loop excitations up, these two endpoints wherever I want. So as Nick just said, he was thinking about an open system where maybe you move one of these off to infinity. Okay? And here we have one of these loop excitations. So this is right here, the only place where the Hamiltonian is frustrated is right here at this endpoint. Well, and also obviously this one. Okay? Everywhere else, the Hamiltonian is perfectly happy. So what that means is when I draw a picture like this, I should also, with exactly equal amplitudes, superpose it with all possible continuous deformations of all these loops and apply all the, well, I guess I've erased it now, all the loop rules that allow me to move around and shrink or get rid of contractible loops. Okay. Yeah. You can, and actually, that's, if I apply a surgery, it's exactly the same as what I drew here. Yeah. Oh, sorry. Is that what by link? This is it's going around both of these holes. Is that what you meant? Oh yeah. You can have one going through the neck. Sure, but that you can obtain that by applying surgery to these two, can't you? Yeah. If I move this around so that it's over here, and move this one around so that it's over here, and then I apply surgery, it goes through both of these holes. Okay. Yeah.
Is A B B minus 1 and B and B B minus 1 the two types of excitation?
Yeah, they're frustrating two different terms in the Hamiltonian. It's two different types of excitation. I haven't drawn this one for you yet. So far, I've only drawn this. Okay. Okay. So now you can also have frustrated plaquettes. Okay. And so a frustrated plaquette will have to invent some way of drawing it because it doesn't have kind of a natural, it's not an endpoint of a loop necessarily. So I'm just going to draw a small square with an x in it. And what this means is, if a Plaquette operator is frustrated, what it means is that if I try to move a loop, actually let me use, so yellow's not a good color. No, let's see what colors we have. Yeah, I think there's a red. So remember, in the ground state, I can move a loop however I like or shrink it to 0. When I have a frustrated plaquette, it means anytime I try to move a loop across here, the wave function has to pick up a -1. Okay, so this is equal to minus this picture. Okay, or again, equals means that particular excited state wave function has to give minus the amplitude for this picture. Okay, so BP, okay, the Plaquette operator tells you, oh, I guess I erased it now. So what the Plaquette operator, maybe I should write this down somewhere where I'm not going to erase it. So what that Plaquette operator tells us is that psi acting on any picture is equal to psi acting on continuous deformations of that picture. It also means that small contractible loops can be erased. And it means that we can perform surgeries like this. Okay, so this is what BP equals +1 is telling you. So if BP equals -1, it means that you have to pick up a minus sign and going across. And so what we have here is there's a particular plaquette at which, if I try to apply the Plaquette flip operator, the Plaquette flip operator will take this curve and flip it over. You have to pick up a minus sign because you have eigenvalue -1. Okay. Similarly, okay, what it also is saying is that at such a frustrated plaquette, it's also the case that if I have a small contractible loop, so here's my frustrated plaquette, here's my small contractible loop, that this is equal to minus the empty picture with no loops in it. Sorry, this should be blue. Okay. So we've got frustrated vertices, which is where an odd number of lines comes in, okay, such as one endpoint. And we also have frustrated plaquettes, which are any plaquette where if you try to move a line through that plaquette, then you pick up the wave function picks up a -1. Okay. Now, you can also have a combination of the two, okay, because after all, you could have a situation like this, where you have a frustrated plaquette and you have, at that very plaquette, you have an endpoint of a loop. Okay, so that's a situation you can also have. That tells you that if you try to move a loop across that plaquette, you pick up a -1, and also the corner of that plaquette happens to have an odd number of loops coming in. Now I've drawn it as that endpoint, that vertex is sitting right on that plaquette, But of course, if you look at everything, if you step back and look at it in a more coarse-grained way, all we're really saying is if you have a vertex endpoint, a frustrated vertex and frustrated plaquette, you can bring them, they don't have to sit on top of each other. If they're close together from a distance, they look like a combination. Yes? Correct. Well, no, you can't actually have that either. So that's a very good question. So how do we get a frustrated vertex? We get a frustrated vertex by acting with a sigma x operator on any one of these links. If you act with a sigma x operator, so if we have here's our little curve. If we act with sigma x, okay, what you do is you create. So you act with sigma x right there, you create two of those. The way to create frustrated plaquettes is to act with sigma z. Okay? So if you have two neighboring plaquettes, and you act with sigma z over here, okay? By acting with sigma z, what you do is you end up creating two neighboring frustrated plaquettes. And then, of course, you can move them far apart. Okay, good question. Okay, so these are the excitations of the system. Obviously, we can create more than one of them. I've drawn just sort of one of each type, or in some cases, pairs of each type. You can have more than one of them. Now, what I'd like to do is connect them to what we were saying about ground states. Okay. Yes. Uh-huh. Okay, good question. So we'll yeah. So we need to make. So you're right. We need to be careful because we need to be careful how we assign phases to different pictures depending on how this sweeps around this plaquette, which is what I'm going to do momentarily. But that's absolutely right. As drawn, this is a perfectly reasonable picture, but it's incomplete in the sense that I haven't told you yet, although you could perhaps figure it out, and maybe you already have based on the question, you do have to worry about how it relates to this picture. Okay. Now, given what we just said, that you pick up a minus sign and moving across a plaquette, the answer is, I hope, is clear that the picture I drew before should receive a minus sign relative to this one, but I'm going to do that a little bit more systematically now. Okay. Okay, now we've just been talking about excitations, but actually I can do the exact same analysis of excited states entirely in terms of discussing entirely ground states. If instead of considering the torus, I considered a system, instead of considering genus, if I considered punctures, okay? So we can also put holes in surfaces. The simplest such thing is the annulus, okay? Or the cylinder if you wish. So here's the annulus. Okay. And all we really mean by putting a puncture in it is there's some region in the center of this disk where I'm not applying the Hamiltonian. Okay. Now, I do have to be a little bit careful about boundary conditions, and we will be momentarily. But if I just look at the annulus, okay, then it's reasonably, then I think you can see that there's sort of two ground states on the annulus. Okay, This is one particular basis of them. And when I draw this picture, what I really mean is I take the superposition over all possible contractible loops inside the annulus, and I write down the wave function that gives them all the exact same amplitude. And when I draw this picture, okay, what I mean is I take the equal amplitude superposition of all of the pictures that are related to that one by getting rid of or adding contractible loops. Okay? So here are two ground states on the annulus. Okay? Now, this is one particular basis, okay? But there's an equally, I would say actually better basis, which is to take a superposition of these, like so. Okay? And if you stare at this for a moment, what you'll see, what I've really done by creating this superposition is if I've taken this superposition with plus 1, okay, then what it means is the superposition with +1 is effectively as if I had even though what I said is by putting a hole here, what I'm really saying is I'm not applying the Hamiltonian. By putting superposition +1, it's basically like applying or requiring the state to satisfy a flip operator even through the hole in the annulus, right? Because after all, the flip operator would move this curve across the hole in the annulus, and then you could contract it. Okay. So in essence, what this is saying is I've got an annulus, I've got puncture here, so there's a disk with a puncture, and this puncture has a boundary condition. That boundary condition is basically the vacuum boundary conditions, if I put a +1 here. The -1, on the other hand, if I try to move this curve through the annulus, I pick up a minus sign, right? Because there's a relative minus sign between these two. So it's like saying I've put one of those Plaquette excitations in the hole of the vortex. So now both of these have exactly the same energy. They're both ground states of the system on the annulus. Okay. So what we could say is that, well, maybe I'll do it up here, that this is like the ground state or ground state plus Plaquette excitation in the center. Okay. So you can see that I can equally well talk about excitations without ever having to talk about excitations, without ever really knowing what their energy is, where they sit above the ground state or anything like that, entirely by looking at ground state properties, but just on ground state properties with the annulus. Okay. And these two correspond to the two ground states, correspond to either, you can morally think of this as being the plus sign is the ground state on the disk, and the minus sign as being the disk with a Plaquette excitation in the middle. But it's not an excitation. This is actually a ground state. It's actually a ground state because it costs no energy because the excitation is sort of going through the middle of the. So the point I'm trying to make is that there is a correspondence here between bulk excitations and ground states on a punctured surface. Such as the annulus. If you're talking only about a single excitation, in fact, you only need to consider the annulus. Yes? Yeah. Yes, we'll get there in just momentarily. Yeah. Now,
I'm worried that you very sneakily broken the symmetry between plus and minus. I would have said somehow like annulus without string plus annulus with string for that has no.
I'm I'm not sure I understand what you're getting at. Yeah. Look. These are. I think what I'm saying is it agrees with what you're saying. Look, these are both ground states, right? I mean, a priori, they're both ground states on the annulus. You have no particular reason to prefer one or the other. I think that's what you're saying, which I agree with. All I'm saying is, if I then want to draw a correspondence between ground states on the annulus and bulk excitations, then the correspondence is +1 corresponds to the ground state, and the -1 corresponds to the frustrated plaquette.
Yeah, you have to make a choice on the right-hand side because there is bulk excitation, which is just do nothing.
Yep.
And on the right-hand side,
Sorry, the right-hand side, there's... I'm not sure. This is what you mean by the right-hand side. Is that correct?
no, you wrote an equation.
Oh, down here? Yeah. Uh-huh.
There's no preferred ground state.
Mm-hmm.
But there's
I agree.
bulk excitation, right? So you have to make some choice.
No. Yeah. Yeah. That's right. Okay. Yeah. So that's right. Thanks. So that, no. Okay. Now I understand what the question is, and that's. And thank you, Charlie, for elucidating the question and giving the correct answer, which is these are exactly degenerate in the limit that the system for this particular Hamiltonian, and for the limit that both the center hole and in particular the center of the annulus is infinitely large. If I were to perturb this even slightly, put it in perturbation like this, these aren't exactly equal in energy if the hole is small enough. Yeah, that's right. I mean, in this case, everything is kind of degenerate, but if you perturb slightly within the same phase, then you can then that degeneracy is broken. Well, they could split them in different ways, but I mean that's true even with the original Hamiltonian, right? I could have made some of these J's negative, which would prefer Plaquette somewhere. So I mean, I don't think that there's, for a particular Hamiltonian, there are canonical choices. If you change the Hamiltonian, those canonical choices change about what you'd call the ground state. I mean, there's still a one-to-one correspondence, but yeah.
Different eigenvalues under
That's right. That's another, yeah. So good. So there's a stacking procedure on the annulus, which is you can take, here's our annulus, and then you can take another copy of the annulus and put it on top of the outside. Okay. So if you didn't know, this is what Mike just said in slightly different language. If you didn't know to put the plus or minus signs there, you could have said, well, I could put any phase, like, why should I put plus or minuses there? But what I can do is there's a stacking procedure on this annulus, which is well defined, which is take your annulus, take a second copy of the annulus and put it on the outside. And you can ask for these states within this two-dimensional basis, you can ask what are the eigenstates of stacking, okay? And those are the two eigenstates with two different eigenvalues, plus or minus 1. Yes? Well, I mean, you can think of, I wouldn't say it in exactly those words, but I would say you can certainly take the torus, you can cut along one of the generators of the torus, and the torus then becomes the annulus. Two of the ground states you get from the torus are the two I drew right here. The other two I haven't drawn yet, but I'm about to. Right, the torus is 4 ground states. These are 2 of them if you cut it open, and I'll draw the other 2 momentarily. Okay. Any other questions? Yes. Yes, I'm going to do that right now. Okay, so for the vertex excitations, we have to allow different boundary conditions. Okay, so when we draw an annulus, we of course have to specify both on the interior and the exterior of the system what the boundary conditions are. Okay, so I drew some things over here. We sort of implicitly didn't let any of these things terminate on the boundaries, but let's now allow that. Let's allow stuff to terminate on the boundary. That's a choice of boundary conditions. There's not a unique way of doing that, but let's for simplicity of drawing, let's set as the boundary condition that we can have a curve and it can terminate at one specific point on the interior and one specific on the inner boundary and one specific point on the outer boundary. Okay, that's just a choice of boundary condition to make life simple. Okay, we could do more complicated things. We could allow it to terminate anywhere. Okay, and then we'd have to consider the amplitude for different termination points. I'm just choosing one kind of arbitrary but simple boundary condition, and we'll see why nothing really is going to matter depend on that. Okay. Well, if we allow, let's say with zero energy cost, something to terminate here, those are still ground states. It doesn't affect anything going on there. But you see, you now have the possibility of a curve that goes from the inner to the outer boundary. If you had taken the torus and cut it open, remember, two of the ground states would come around that way. You would also get, when you cut open the torus, you would also get situations like this where the torus cuts through, where your cut cuts through one of the lines. And you can see that you would have that picture and that picture. Okay? Plus all the continuous deformations of these and adding contractible and non-contractible loops. Okay? So these are the two other grounds. These are the two other types of excitations. Again, we can make linear combinations. Okay, here are two linear combinations. Okay, I think this partially answers the question about. So again, this linear combination with a plus sign, we identify with a vertex excitation. With a minus sign, we'd call it a vertex plus a plaquette excitation. Okay. The reason being, so again, this with a plus sign looks exactly like what you expect a vertex excitation to look like, that basically you can move stuff through and move it around. It's just two endpoints, and the endpoints of the two vertex excitations are required to be at the inner and outer boundary of the annulus. With the minus sign, it answers a question we had about, well, was this picture a little ambiguous? Now we've specified specifically what that phase is. Okay. Now I've drawn this going around this way. Okay, but we know that surgery. We know that this surgery over here actually tells us that we could just as well do a surgery here and go around the other way, and that makes no difference. Okay. Now, these two linear combinations, you can see, have eigenvalues plus or minus 1 under a 2 pi rotation of the interior boundary of the annulus with respect to the exterior boundary. Okay. If I do that 2 pi rotation with the plus, and in the state with a plus sign, nothing happens. If I do it with the state with a minus sign, we pick up a minus 1. Okay. So what we see is that under a twist, these two types of excitations, or in this case, these two ground states, okay, have different eigenvalues under a twist, okay, which in this, it's called a Dane twist, okay, if I were thinking of it. Sorry, Dane twist. This is an example. This is kind of a physical example of a Dane twist, okay. Normally you think about Dane twist perhaps with the torus, where you cut as we just discussed, obtaining the annulus by cutting open the torus. You would cut open the torus, twist by 2 pi, and then glue it back together. I've kind of skipped the middleman I've only got the middleman here without the cutting and the rejoining, but this is essentially a Dane twist of 2 pi rotation of the interior boundary of the annulus with respect to the exterior boundary. And the two types of excitations have eigenvalues plus or minus 1 under those kinds of twists. So we have here all of the excitations of the system, or the 4 types of excitations that the system has, But we can do this entirely talking about ground state properties. Okay. We don't ever have to mention anything about excitations. We don't have to worry about what the Hamiltonian looks like up at high energies or anything like that. We can just talk about ground state properties. The price we pay is that we're considering not just the torus or the two-handled surface. Instead, we're considering surfaces with punctures, such as the annulus. Okay. Any questions? Okay, so it's also, in that spirit, we can also consider, rather than the annulus, we can consider the disk with two punctures. Okay. If you consider the disk with two punctures, okay, then you can also start asking about what happens to these kinds of excitations. Okay. In particular, so let's suppose we may need to allow two different points on the boundary where these things can terminate. Now we've got two excitations, okay? But now these two excitations we can apply surgery to. And now we see, if we apply surgery to two of these excitations like this, then actually, if I draw a dotted line around here, you can see there's no line coming out. Okay, so as far as a measurement over here is concerned, we would say that there's no vertex excitation in the interior. Okay, so there's no line coming from the inside to the outside. All we've got is something local. Okay, as far as this is concerned, there's some local excitation within the interior. There's some excitation of the edge over here, but there's no vertex excitations as far as this measurement along this dotted line is concerned. So two vertex excitations, the technical term as Nick introduces fusion, two vertex excitations look like zero vertex excitations. Okay. And by drawing similar pictures, you can also convince yourself that two of the Plaquette excitations correspond to a single, to zero Plaquette excitations. These vertex excitations, this model, are generally called E or electric excitations. These are usually called magnetic. And then the combination of the two so the combination of the two, this thing with a minus sign, okay, is sometimes called EM or sometimes psi. The reason for the psi is to denote the fact that it's a fermion. Okay, its twist is -1. You rotate it by 2 pi, you pick up a -1. That's a property we expect of a fermion, so sometimes called psi. Okay. Okay, so actually you can also, by similarly drawing pictures, okay, we have two of these excitations. You can actually ask what happens when I take one of these through and bring it around, which forces you to drag this around. You can apply the rules and find non-trivial braiding statistics as well this way. Okay. I'm not going to go through that in detail right now, but I think I'm supposed to assign you exercises. Okay, so compute by drawing pictures, the phase associated with the exchange, or actually not the exchange, with winding an E around an M. Okay. Now to do that, it will be essential that when you write down the M, you write down this thing with that minus sign sitting there, and that when you draw your E, you're going to have to draw your E as being this thing with a minus sign over here, plus sign over here, sorry. Actually, in this case, you'd get the same answer whether you use the E or the psi. So when I've drawn one picture for you here, but this is actually 4 pictures, okay? Because each of the particle types really is a superposition of 2 of those pictures. You'll have to draw 4 pictures and deform those pictures continuously. When one of these boundaries moves, it drags the blue line around with it. And then you'll have to apply, to get the final answer, you'll have to apply these rules to compute the phase that results. Okay. So you'll have to do a little bit of drawing of 4 pictures and moving stuff around to find the answer. Okay. Okay, so with that example under our belts, I would like to now step back and try to abstract definition of a topological phase. Okay. So we've seen an example, and really what we're trying to do now is what is the general phenomenon of which this is an example? Okay. So topological phase is a system where you have a local Hamiltonian H. Okay. We had that, right? The Toric code is a local Hamiltonian H. Such that there exists a delta, an energy delta, and a length scale C. So this delta is an energy. C is a length. Okay. Such that the limit, if I take the limit of the system size going to infinity of delta, this is some non-zero value. Okay, so I take the system size to infinity. The energy gap delta has a non-zero limit. As I take the system size to infinity, this correlation length also has a finite limit. Okay. Then if I look at the energy eigenstates with energy E less than delta, so I have a non-zero. So you should think of this energy as the bulk gap. Okay. So this is an energy equals bulk gap. This length you should think of as the correlation length. Okay. So I have energy eigenstates E. So I have a finite number. Okay. Let me be a little careful. This is a 2D topological phase. I have a finite number of energy eigenstates, E less than delta. Let's call them 1. Okay. That subscript sigma is giving voice to the fact that the number of these states depends only on the topology of the surface sigma that the system lives on. So that means both the number of handles and the number of punctures. Okay, that completely for an orientable surface, that completely specifies the topology of the surface, the number of handles and number of punctures. So the topological phase has to have a local Hamiltonian. It has to have a finite bulk energy gap and correlation length such that there's a finite number of energy eigenstates E less than delta, and such that for all local operators x, this is just constant up to corrections of order e to the minus L over c. Okay. So what this is saying is, if I plot what the spectrum looks like, that here's this energy delta with a finite limit and the thermodynamic limit. And then down here, there's a finite number and sigma eigenstates. The number of those depends on the topology. So this is energy in this direction. Okay. The number of these depends on the topology. Okay. And if I take any local operator and take its matrix elements between the states here, then we just get a constant up to exponentially small corrections. By assumption, the Hamiltonian is a sum of local operators. So the Hamiltonian is a sum of such terms. So this also tells us that the energy splitting here is order of e to the minus L over c. Okay. Now, the Toric code, Hamiltonian that we just discussed, satisfies these. Okay? We just looked at an example of this. So if you remember, let's consider, for instance, the torus. Okay? On the torus, we had 4 ground states corresponding to those 4 winding numbers, modulo 2 around the torus. Okay? There's an energy gap, which is basically whichever is the smaller of J1 and J2, or twice that is the energy gap, okay, above the ground state. So there's a big energy gap over here to all the excited states. The energies below it, the states below it, there were 4 of them. That number only there were 4 of them on the torus. There was 4 to the G on a genus G surface, so the number only depended on the topology of the system. No local operators could distinguish these different states. Okay, so for instance, if we were thinking of, let's say, the Ising model in its low temperature phase, which has 2 degenerate states up and down, mostly up and down, well, those are distinguishable by local operators. Not the case here. The splitting in the Toric code was exactly 0. Okay, but that's a special feature of the Toric code. If we perturb that system a little bit, if we perturb the Toric code a little bit, then indeed we would find that there was an exponentially small splitting in system size. Yeah. Okay. Okay. I'm halfway done. Yeah. I'll wrap up. So I just want to. I know well, but I'm supposed to give them homework, right? So I should give more exercises. I'm wrapping up. This is the conclusion. So So it's also important that no local operator be able to distinguish. So obviously the Hamiltonian is an example that no local operator be able to distinguish. Okay. Now, if you remember what all these ground states looked like, the way they differed was in terms of winding numbers modulo 2, something that you can't determine locally. So the local operators can't determine the ground states up to, exponentially small stuff. Because again, if I look at winding number even versus winding number odd, they basically are indistinguishable, but in a finite system size, you might be able to notice a slightly higher density of loops coming through at a given point for the odd versus even. Okay. So anyway, so that is pretty much where I'm supposed to wrap up today. Are there any questions? Yes. Yep. Are you asking about specifically this picture here? Yep. Yep. Yeah. Uh-huh. Yeah, I mean, you certainly yes. The answer is your question is yes. But I think what we want to do here is just, I mean, we can certainly think of two, but we can sort of look at them separately. We want to think of the excitation here as being on the inner boundary, and this outer boundary being very far away. So really, you have one at the center and a second excitation at infinity. They have to come in pairs. And the same thing is true here. You think of an excitation here and another excitation at infinity. Yes?
So the toric code, there's no exponential splitting at all.
Well, C is 0. The correlation length is 0 in this case. So there had to be a finite correlation length. It wasn't allowed to go to infinity. In this very special case, the correlation length is 0. If you perturb it a little bit, it'll be a finite correlation length. And if you perturb it a lot, that correlation length will start to diverge when you hit a transition.
Wait, so the correlation length.
The correlation length being 0 is because it's a sum of, well, yes. I mean, I would say the correlation length is 0 because it's a sum of commuting terms, yeah, which is why it's exactly solvable. Commuting local terms, yeah. Not that I know. I mean, in this case, maybe, but for the reason I just said. In general, no. Yes.
Is this property of local observable? That's a definition you just defined.
Yeah, this is a definition. 2D topological phase definition.
And I guess I missed. You must have said it, but I missed. Why is that the definition?
Oh, yeah, so I guess the philosophy I'm taking here is we have this example, the Toric code, and what I'm trying to write down in a definition here is I'm saying, okay, we have this example of something cool. Let's try to find kind of abstract the key properties that generalize. So these are the properties of the Toric code that generalize to a whole host of things. Tomorrow, we'll see other examples that satisfy this and see what the general structure is that follows from this. I'll say it's not unique. There are other ways of defining a topological phase. I like this one because it's useful, because it sort of puts kind of the most physically kind of manifest properties, which is a gap, a correlation length, and indistinguishability of ground states kind of in the front. You definitely can consider other definitions. Yeah.
I guess I now remember. Nick said
Yeah.
this. I mean, if the last property wasn't true, then you could add that to your Hamiltonian as a small deformation, and now you split the degeneracy.
And I split the degeneracy. That would certainly also be true. Yes.
Basically,
Yeah.
same as fun.
Yeah.
So, Nick was asked
Okay.
this question too,
Okay.
But in your definition, you didn't really use 2D.
No, I did not use 2D. That is a good point. Yeah, so I didn't. I'm not sure if this is too restrictive for 3D or not.
Might be questions when you get to talk about topological stuff.
Yeah. Yeah.
It's a more complicated question.
Yeah. 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 For instance. Yeah. I mean, you're right. This definition does have a very natural generalization to arbitrary dimension, but I think it might be too restrictive in higher dimensions, or that would be one concern, potentially. Yes. No. The correlation length is not a measure of how long you can make this loop. The correlation length is, well, it's, in the Toric code, I never really had to mention the system size, right? But if you perturb it even a little bit, things will depend on system size. And a correlation length is basically saying how big does the system have to be for it to look more or less like morally like a thermodynamic limit. Okay. It's clearly if you make the system small enough, then of course there's no phase transit, right? And phase transitions and the notion of phases is purely a thermodynamic limit statement. So really the correlation length is how big is big enough. Yeah, you can get rid of it. You make the system small enough, then all of this goes away. Absolutely. Yep. Yep. Oh, yeah. So I see what you're saying. If I got rid of this condition, so if I mutilated my Hamiltonian and got rid of this one right here. Yeah. If I were to get rid of this condition here, then you see this condition is what tells me that I should consider on the torus only winding numbers modulo 2. But I could modify the Hamiltonian so that it no longer in the ground state impose such a condition. Then all winding numbers are allowed. So then the degeneracy is L squared, where L is the length, or L1 times L2, where those are the two lengths of the two x to the torus. You know, if you get rid of this, it'll also be gapless. So it's not really a topological phase. I mean, this is where you get into the issues of what do I want to call a topological phase. It would no longer be gap. It would no longer have a gap. We have an infinite degeneracy. But the degeneracy between these ground states would be exponential in system size. And the things above the gap would be power law in system size. So it's an interesting state with topological properties. It's just not something that would satisfy this.
Why can't I also imagine a gap system with infinite degeneracy? Or am I not allowed to do that?
I think you're allowed to. I just think that such a thing is very fine-tuned in general. What's that?
We don't seem to know any examples.
Well, they're trivial things you can write down with huge degeneracy, like just take the Hamiltonian equals 0. All states are, equal energy. It's extreme, but you add any perturbation, it's going to split that. So.
It may fail to satisfy the condition on top.
Well, I mean, look here. I specifically put in finite number as.
I know,
But I think you're right. Yeah, it wouldn't satisfy this. That's right. So I think it's going to generally be true that if you. Yeah. Okay. So the answer to your question is I can't prove that such a thing doesn't exist in 2 or more dimensions. I don't know of any examples. It would be interesting if there are. Okay. Yeah.
Let me just make a quick announcement. We're running a little late,
Yeah.
so we're gonna delay the next lecture just so we have a little bit more time for lunch until the But all subsequent lectures we're gonna be a little bit more